Thanks very much, and thank you for the opportunity to present today at the workshop. As you can see, I'm representing the Barcelona Supercomputing Center today. However, I only joined the center about 2 weeks ago. My background is in computational physics, particularly condensed matter theory and DFT, and also in HPC. So I'll be talking today mainly about work that I've undertaken prior to joining BSc, and that works at the University of Cambridge, and working on a particular DFT code there that I'll be talking about in detail. So I thought it would be remiss of me, despite the audience, to give a talk on density functional theory codes without at least a very brief introduction to DFT itself. DFT is, of course, popular for its acceptable accuracy and acceptable cost. At the heart of DFT is, in the formalism that I'm considering, is a set of n nonlinear eigenvalue equations, which, as I've written here, all of the symbols have their usual meanings. H is the Hamiltonian matrix, which is a function of rho, the density, and phi is an eigenstate of the Hamiltonian. I've labeled the eigenstates with B because I'm considering mainly the solid state context, and so B stands for bands. And clearly it's a self-consistent solution that's required. And the distinction that I'm making in the approach to DFT computationally is in two main categories: order n being linear scaling with the number of electrons in the system, and cubic scaling, which is what I'll be focused on today, and how we can meet the demands of exascale, or edge towards the demands of exascale, in cubic scaling DFT. So the code that I'm going to be talking about mainly is CASTEP, with which some of you may be familiar with. CASTEP is originally based in the UK, developed in the UK, and it uses a plane wave basis, as I said, and so is traditional cubic scaling DFT. It's scalable to thousands of cores, primarily through distributed memory parallelism via MPI, but also through OpenMP, and more recently OpenACC, which I'll talk about imminently, the move to that platform as well. And being a plane wave basis code, of course, the FFT is the primary means of leveraging the efficiency of the basis, moving between the native Fourier space and direct space to apply various matrix operators to the eigenstates, or the trial eigenstates. And essentially these can dominate the computational cost in one way or another. So the work that I've particularly focused on, and the recent developments that I'm going to focus on in the talk today, are to do with optimizing the parallelism of the FFTs in one way or another. And I'll focus on the details of how the parallelism is or isn't edging towards rate of strong scaling for exascale machines. Just before I go any further, I just want to be clear on the dimensions of parallelism in a plane wave basis, or particularly in CASTEP. The main object is the eigenstates of the Hamiltonian. This is central to all the computation. And as you can see, the phi here has acquired an extra label from the B, which is B still is an eigenstate, but K stands for a K point, which is just a sample point in the solution space. The number of bands, the number of eigenstates ranges in CASTEP from, say, orders of 100 for a small to medium-sized system to, say, 1,000 for a larger system. And we can parallelize over the bands, although there are limitations to that, mainly due to overlap integrals in matrix elements that can limit the scaling due to the comms that's required for orthogonalization of the eigenstates. The K points, on the other hand, offer the most opportunity for strong scaling because the equations over K are very loosely coupled. However, as the system size increases, the number of K points reduces to 1, and so it becomes a null, it becomes a moot point for parallelization. And so what I'm particularly interested in is the Fourier components, or the G vectors, as I'll be referring to them, and these offer the most scope for large process counts, and therefore strong scaling, or at least the opportunities for strong scaling. In CASTEP, you'll typically get something of the order of 10 to the 4 for a small to medium size system, and then up to 1 million for something larger. So the 3D FFT grid over which we operate when it's memory distributed becomes, of course, involves free 1D FFTs and then 2 grid transposes, which are performed via all-to-all V in our case. And I'll be talking about the problems associated with that, the well-known problems associated with that in the forthcoming developments. So let's begin with the first of these, which is porting CASTEP to GPUs in particular, but accelerators generally, to try and leverage the performance of heterogeneous computing. We currently offload 2 major bottlenecks to GPUs. One is FFTs, although not using memory distribution, G vectors, and the other is matrix multiplications, particularly in the application of the non-local pseudopotential operator. Now, the FFTs are really only a bottleneck in small to medium-sized systems. At scale, the FFT kernels themselves are negligible. The matrix multiplication, on the other hand, can be a bottleneck regardless of the system size, although of course diagonalization is the major bottleneck in DFT codes. As yet, we haven't been able to offload that successfully, or efficiently, I should say, just simply due to the sizes of the matrix for diagonalization relative to the transfer costs. Although I think that is changing soon with the optimizations that we've made, and also the NV-link becoming more readily available, and so on and so forth. But anyway, as yet, these are the 2 major bottlenecks that we've looked at. And our port is an OpenACC port, which we use for the allocation and deallocation of device memory, and also transferring the data. And then we leverage the power of the libraries and so on, as well as optimizations ourselves in OpenACC. And one area that I've been particularly interested in is the acceleration of so-called hybrid exchange correlation functional calculations. These are an important class of calculations. They offer a greater degree of accuracy relative to other exchange correlation functionals for particular systems. And the reason that I've been particularly interested in them is, well, for my own research interests, but also because they provide an opportunity to showcase the capability of the CASTEP GPU port. The reason being that in a hybrid exchange correlation functional calculation, the runtime is almost entirely dominated by the FFT kernels themselves, regardless really of the system size, or at least to some extent, regardless of the system size. And the reason for this is that the number of FFTs scales quadratically in the number of sample points and also the number of bands. So, so essentially, if you optimize the runtime of the FFT kernels, you optimize these kinds of calculations. With that in mind, what you can see on the in the figure here is a comparison of the speed up of CPU versus an initial GPU port versus a final refactored GPU for these particular kinds of calculations. And this is the time per SCF cycle, the SCF cycle being the main loop in DFT and CASTEP codes. As you can see, we get an impressive speed up, as we might expect. The CPU relative to the initial GPU port gave us around a factor of 10, and that's pretty much just by giving the by offloading the FFT kernels directly to the GPU, and the acceleration comes from there. Very, very limited other optimizations that we performed, but then refactoring the code again, looking at extending data locality and so on and so forth, we're able to get up to 16 or 17 times for these kinds of calculations. And looking at this from a slightly different point of view, the figure that on the right here is the refactored GPU port bandwidth, which, as you can see, is approaching 700 gigabytes or so for the kernels that we optimized, including the FFT library kernels, but also others, as I said, auxiliary kernels to those. And the maximum bandwidth that we measured on the system was around 800 gigabytes per second. So we're confident that we're approaching the optimum for this particular class of calculations here. Now, there's an important point to make, however, with this. These calculations were performed on the Ascent system. The CPU is 1 MPI process and 21 OpenMP threads. We're only using a single K point here, a single sample point, but we get this kind of speed up if we, similar anyway, by parallelizing over multiple K points, because as I said, the coupling between the sample points is very weak. Now, using 21 OpenMP threads in CASTEP is really perhaps not quite a fair use of the parallelism. It doesn't scale well with that number of OpenMP threads for one MPI process. But nevertheless, the reason we chose this was because it uses one full node of Ascent. So therefore, we can compare one full node with Ascent with the CPU and GPU combination, which is literally one MPI process attached to one GPU via the GPUs here V100s with NVLink2. So as a proof of concept of targeting a particular set of calculations, which we're confident we can parallelize over in terms of K points and to some extent bands, but not G-vector parallelism necessarily, and being able to offload a computational bottleneck to the GPU, we've achieved our goal. However, there are numerous challenges relating to this that I'll now talk about. So, first of all, Fortran, OpenACC, CASTEP is a Fortran code, almost exclusively a Fortran code. And we chose the OpenACC platform because the platform is mature in terms of acceleration relative to, say, OpenMP. It's also an open standard relative to, say, CUDA or something of that nature. There's multiple compiler vendor support, which is an important feature in terms of people being able to actually use CASTEP. And as I think we demonstrated in the previous slide, we can achieve comparable performance to CUDA if we know what we're doing and we target the right kinds of calculations. I should point out here as well, for the semi-local and local exchange correlation functional calculations, we get something like a 2 times speed up relative to the CPU. So it's very significantly different from what we just looked at, but to be expected, I think, because of the difference in the kinds of bottlenecks that we're addressing with the accelerator. So the OpenACC platform has served us well in some respects, but perhaps not so well in others. There are limited feature sets in the OpenACC compilers for Fortran. Yeah, I'm talking specifically about Fortran here. And just as an example, the NVIDIA HPC compiler, NV Fortran and so on, lacks support for device-only allocations. For those who are interested, the device resident clause actually aliases to create, so you end up with an allocation on the device irrespective of what you've actually put into the code. Now, the reason that I mentioned this isn't to complain about a particular compiler or anything of that nature, but rather to draw attention to the fact that what does it say about the future of Fortran accelerator compiler support if such a large player in the accelerator space as NVIDIA is not providing support for such an important part of the OpenACC standard. And you may say, well, it says that Fortran is dying or dead, and therefore we should move on from it. But the fact is, CASTEP is a leading electronic structure code, and it's written almost entirely in Fortran. The same can be said for, say, VASP. It certainly uses a lot of Fortran. The same can be said for ABINIT. The same can be said to some extent for Quantum Espresso. The same can be said for Siesta, which is a linear scaling DFT code, and so on and so on. And I know all of these are not using OpenACC for their acceleration, if they do have acceleration, but still, the point is that where does it take the future? I don't have an answer for this, but I'm hoping maybe it will provoke some discussion after the talk. One other thing to notice here, which will be relevant soon, is that there's no CUDA IPC equivalence as yet in OpenACC, certainly not one that's been implemented in Fortran readily. And this tends to bloat host-to-device transfers and can limit the system sizes that we deal with. And why this is particularly important is because, as I've said, G-vector parallelism is really vital to maximize the parallel scaling of CASTEP and plane wave DFT codes in general. So the problem that we're meeting in the development of that is that the CUDA-aware MPI efficiency is reduced by the overhead of the buffer preparation on the device. This is all about device data. We're not talking about host-to-device transfers at this point. And the problem here is that the number of non-vectorizable kernels grows in proportion to the size of the MPI communicator over which we're performing the all-to-all, the MPI collective. And the reason they're the fact that they're non-vectorizable means that they run particularly slowly, of course, on the device. And then on top of that, in a plain wave code where we have distributed memory, FFTs, then we're typically dealing with small numbers of data points being transferred from one process to the other in the communicator. And so we have low computational intensity of the kernels. So these two things just tend to undermine the efficiency of the CUDA-aware MPI. Of course, it's much worse without the CUDA-aware MPI, but still, it's not a panacea to these kinds of problems. Of course, if we had CUDA IPC equivalents in OpenACC, some of these problems could be avoided potentially, but there's no support for that, so we have to try and get around it in some other way, at least at the moment. And just one other thing to mention here, the performance that we saw in the previous slide for the FFT kernels really relies on the batching of the FFTs, because, as I say, we're dealing typically with the data sets simply aren't large enough to saturate the device. And so we have to batch them up in order to get the computational intensity up to something that amortizes the data transfer. But the repackaging of these, when we come to G-vector parallelism, we have to repackage the data into contiguous buffers. So all we're doing really is adding more low intensity kernels and increasing the memory footprint. So these are significant challenges that we have, at least in our Fortran OpenACC port at the moment. There's active work to address these. They're not necessarily insoluble, but I'm highlighting them because they are issues that we need to address. Okay, I'll move on now to the second of the developments that I've looked at, which again is related to G-vector parallelism, but here I'm talking about only on the CPU side of things. This is independent of the GPU port. And I'm also not focused at all here on hybrid XC functional calculations. I'm talking entirely generally about CASTEP and its performance. As I mentioned earlier, we deal with typically relatively small data sizes being passed in the MPI collective. So if we scale using G-vector parallelism, we're typically in a latency bound regime, which is obviously for an MPI all-to-all collective going to lead to quadratic comms, and the comms limits the strong scaling of the code, which is just demonstrated in this slide here, where if you look at the bottom slide, you can see, or the bottom rectangle rather, you can see the comms. This is comms only from the all-to-all V in FFTs, and you can see that as a percentage of the total wall clock time. Even scaling from 64 to 1,000 cores here on a reasonably, I would say, a medium-sized system. We've got 270 atoms in this system. The comms is reaching 50% or so of the total runtime, and obviously nullifying any parallel scaling beyond that point, or sometime before that point, in fact. So this is what we've tried to address in our development, and that's what I'm going to talk about now. So the solution to this is well known, really. What you do is, in principle at least, is just to take your effectively 1D chain of processes and map them to your FFT grid and some 2D logical process grid. The reason why this is efficient, of course, is because then in the all-to-all in the process grid, if you can find the all-to-all to the columns or rows of the process grid, then you're dealing with about root n processes, So when you get the quadratic scaling of the all-to-all, you actually end up with linear order in the number of processes, in the comms due to the processes. This is of course well known. It's established in other fields, but has been proposed numerous times over the years in plane wave DFT codes, but to the best of our knowledge has not been implemented, at least not at scale, in any widely used plane wave DFT code. And perhaps one of the reasons for this is because the use of the logical process grid has issues for the load balancing of the plane waves in the G-vector parallelism in a plane wave DFT code. And what I mean by that is that CASTEP uses a 2D domain decomposition, with simple schematic of that here, of course, and the fine-grained load balancing is complicated by having a native spherical native Fourier space, which is what you can see in the right-hand figure. And what we've got is the sphere here is where the eigenstates of the Hamiltonian are defined. But as I've written it here, this is in a real space or direct space representation, but their native space is in fact the Fourier space. So we have them in this compact format, but in order to compute the density, we do this in real space, and because the density goes as the magnitude squared of the eigenstates, we have to expand into a cube, the volume of which is 16 times greater than the sphere in which we started. Now, clearly, if you superimpose the 2D domain decomposition onto this cube, or indeed onto the sphere, I should say, not the cube, you're going to end up with a load balancing issue. And there are numerous ways in which this has been addressed over the years, but there's not really been a robust, provably optimal way that this is being addressed, and certainly not in conjunction with a 2D logical process grid implementation. So what we've done is to develop an algorithm that does indeed optimize the load balance and provide the optimal comms via the 2D logical process grid. What you can see in the top two slides here is the default unoptimized, if you will, distribution in CASTEP. This is the G-vector sphere, so this is a Fourier space. Just a toy example of 6 processes. Here's the load balancing, but this is what it would look like in CASTEP. And what you can see at the bottom is the optimized G-vector sphere distribution and the accompanying load balancing here. And the important point to take here really is that in the top we have a load balance of a factor of 2 between the least and the greatest, whereas in the bottom side we have a factor of about 1.4. And more importantly, the load balancing in the top is the default load balancing scheme in CASTEP, whereas the one in the bottom is our new algorithm, but this is provably optimal and it's robust. So effectively, we have indeed optimized the load balance. We're confident in saying that, and then we can implement the 2D logical process grid to then address the comms as well. So what does this look like in practice? As I said, this is just as an illustrative example, but in practice it looks something like this. So here, the system that we run on, the HPC resource system that we run on, is Archer 2, which is a UK tier 1 system. It only has CPU support only. It's not a heterogeneous system. And so on the bottom axis, you can see the cores there. And then on the vertical axis, it's the time for 10 SCF cycles. So the time for 10 main loops of the code. And the figure at the moment is showing just CASTEP, pure MPI. And you can see for this moderately sized system in CASTEP, we're bottoming out at around 512 processes, after which there's no point in further parallelism. If we introduce some OpenMP threading, 4 threads per process to this, we can extend the parallelism to around 1,000 processes. One of the reasons for this is that we are only having 1 in 4 of the processes involved in the all-to-all, so we're significantly reducing the all-to-all comms bottleneck there, also accelerating other parts of the code as well through the OpenMP support. But still, we're only getting to this 1,000 core limit here. And if we introduce the grid, then okay, this is pure MPI, no threading, and this is without actually implementing the sub-communicator comms. This is just effectively the load balancing that you're seeing, and you can see immediately that we extended the scalability just of the pure MPI to around 1,000 cores, after which there's a steep gradient there as it falls off. But if we introduce the sub-communicator as well for the pure MPI, now we're extending it to around 2,000 cores. So if you compare the sort of pink line here to the dashed line that we started with, we've gone from 512 to 2,000 or so. And then if we go one step further and now introduce the, so we now have the full complement, if you like, of the process grid working with the sub-communicators and the load balancing with the threading of OpenMP as well, we can get to around 4,000 cores, after which we actually run out of data with this particular example, so we can't extend the scaling any more than that. But as you can see, there's considerable room here for optimism in how we can progress with this. And there are several optimizations we've yet to do. This is only a prototype implementation, really, of the algorithm that we've developed. Having said all of that, there are significant challenges still, of course. What I've just talked about is extending the strong scaling of the plane wave DFT code for a moderately sized system to around 4,000 cores. Well, that's not going to get us to exascale on its own, quite clearly. Although it's positive, it's not a solution. So very briefly, I'll just pose a few questions, really. Can we redesign and optimize existing algorithms? One example of this that relates to the GPU port that we were looking at earlier is the adaptively compressed exchange formalism. Some of you may be familiar with this. This is particularly GPU friendly, and we've implemented this in CASTEP and it works well, but it really requires CUDA IPC equivalence in order to optimize it. Also, is there a possibility of introducing new dimensions of parallelism? One area that's under active research in CASTEP is to implement shift invert methods for solving SCF cycles. I'll say no more about this because my expertise in this area is very limited, but still, it is an area of active research. Also, I think importantly here for the CASTEP strategy is similar to the GROMAC strategy that was mentioned in Erwin's talk, where we're talking about, can we achieve exascale in the code itself for our core computation? No, perhaps we can't, but we can adapt our workflows and so on, and therefore move to more cores that way. And finally, the question still remains, should we just rethink from scratch, as is sometimes said about plane wave DFT? Do we need to rethink the algorithms from scratch? where is the future of all of this going? Can we achieve what we hope to achieve, or do we need to be do we need to take a longer look at ourselves and say, well, perhaps this can only work at up to some particular scale, and we won't get to the exascale with this form of DFT. Well, anyway, these are questions which I hope will at least provoke some discussion or some thought for after the talk. What I'd like to do finally is just say thank you to Dr. Phil Hasney, who I think is in the audience today. He's been my PhD supervisor. He's a CASTEP development, part of the CASTEP development group, and also at the University of York. He's been, of course, instrumental in the work that you've seen here. And also just thank you to all of you. That brings me to the end.
Thank you very much. So I've seen that there's already a question in the chat by Erwin, who's asking if you tried the CUDA Fortran instead of OpenACC.
Yes. Yes. Yes, some of the development that I've done has been using CUDA Fortran. I think one of the issues there is you're tying yourself, of course, into one particular vendor. Also, the support for that itself is not isn't that fully featured relative to CUDA C. And of course, the maintainability of the code also becomes an issue. You've got your CUDA being developed alongside your CPU Fortran, and so there are issues with that I think can lead to problems there.
If I may ask a question also, so I mean, it's a bit in the line of the one that I asked to Erwin, and it's related to your last question. I mean, and I think I'm convinced about that, we go to large scale computing and don't distinguish high throughput and high performance computing. Yeah. And I mean, okay, is it really useful to invest so much in changing the code to adapt to something when in the end to answer a given question, because we have to answer a given question and not a given simulation, we need to do many simulation, which can be in a sense high throughput. And so maybe it's worth investing in things that, as Mattia was pointing, require that once maybe a job is finished, it's reassigned a new job. Once a job is finished, the nodes are reassigned to another job. That might be a bit more, you know, I wouldn't say useful, but more in terms of invested time to reward more important.
Yeah, absolutely. I think this does relate back to what Owen highlighted in the GROMACS strategy, where we're looking at trying to optimize the core computation within the code, but also how can we then exploit for different kinds of calculations, how can we exploit massive parallelism by as you say, perhaps a good example here is phonon calculations, where you can distribute the work over different dimensions of the calculations and so forth. And then also in active development in CASTEP is automation of the parallel strategy and how that should be used in relation to a given hardware set at runtime. So all of this is working towards that kind of goal, but I think it's vital to actually get the optimal performance from your core calculations in the first place, and to say, well, that is now effectively a solved problem, so what else can we do?
Yeah, because I mean, I didn't mind. So sorry, I went and then I'll leave you ask a question. I mean, I didn't mind something which, in the end, I mean, you're going to do a number of calculations from which maybe you're going to do some machine learning, and your final answer depends on a number of calculation, which are in some way independent from one another. Well, not in some way, they are independent from one another, though they are connected to the fact that they are helping you to answer a question, you know, and this is maybe the idea of the workflow.
Yeah, yeah, I agree.
Okay. Okay, Owen.
Yeah, I just have a comment that actually Matthew just said as well. Yes, we need to look at these ensembles and how to run them as efficiently as possible, but we must not forget the single simulation efficiency over that.
Of course,
this is still core, and because the resources are still scarce, right? And we have to share them with many others. You need to be as efficient as possible, and then you can start dealing with the efficiency of the ensembles.
Sure. But there's no way.
Again, there also is, I think this will be a place where a lot of AI technology can have a role.
Yeah, because there's no way you can beat independent jobs. So if you have a number of independent jobs that are needed to then do some kind of machine learning, yeah. I mean, there's no way you can go faster than independent, basically. Other questions? Okay, so if not, we're about at the time where we can stop for half an hour and we reconvene for the last talk by FAIR-DI. Thank you all very much.